faculty member in 90 to 94, and then I came back in 1997 as department chair there, and Dr. D. Sengupta and his wife was there for a workshop. So we're excited. He's really a father to me, really, because he really loves mathematics like I do. So that's what I really like about our relationship. So I would like to have Ms. Marquette come up from the Department of Vice Chancellor of Academic Affairs to give us a welcome and remarks from Dr. Newkirk.
Okay. If I can stand right here. I do bring you greetings from the Division of Academic Affairs here at Elizabeth City State University, where Dr. Van Newkirk serves as the Provost and Vice Chancellor. I am certainly indeed pleased to be here to join in the celebration of Dr. Sengupta's 60th birthday as a former student, mentor, mentee, I guess I was. He's a former professor of mine, a former mentor, and now a colleague. And I certainly do wish you the best on this day. Congratulations, and just enjoy your day.
Thank you. We're going to get the show started here. Our moderator this today is going to be Ms. Elizabeth Reed. She is a 1988 graduate of Elizabeth City State University for her bachelor's degree in mathematics, as well as she has a minor in English and a minor in physics. She got her master's degree in mathematics here at Elizabeth City State University in 2013, and our moderator, Elizabeth Reed.
It's my privilege to introduce our first speaker, our very distinguished speaker for this afternoon, Dr. Johnny L. Houston, who is Professor of Mathematics Emeritus right here at Elizabeth City State University. He has degrees in mathematics from Morehouse College and Clark Atlanta University, as well as a PhD from Purdue University. He studied for a year in France and then spent several years working at universities before joining ECSU in 1984. He has a very impressive career. He was Executive Secretary of the National Association of Mathematicians for 25 years. He's been the author of several books and numerous publications. He has done presentations in all 50 states, 55 countries, and 6 continents, which, to my count, is everything except Antarctica. He has received over $15 million in grant funds and more awards than I can list. So please welcome Dr. Houston as he speaks to us on the wonderful world of the mathematical sciences.
Good afternoon.
Good afternoon.
I just lost a minute. So, yes, good, thank you. First of all, it is indeed an honor for me to be here today. honored for a number of reasons. First of all, I had the privilege of helping to nurture this department to where it is today. And I started here in 1984. And when I started in 1984, they told me they had hired another mathematician that year. I said, oh? I said, where is he from? They said, he's from upstate. I said, good. And then I found this mathematician, I talked with him, and I found out he had a wife who was also a mathematician, who was also. So we came to be friends, we came to move along the way. Dr. Sengupta and I started at ECSU the same year. And it was my pleasure that the kind of professionalism that he brought here, the kind of quality of teaching that he brought, and the kind of research was very inspiring to our students, very inspiring to faculty members who were in the situation with us, and that it was, and so I'm honored to be here to help celebrate his 60th birthday. Now, when he came, he was the junior. I'm over 70 now, so I was older than he was. I had been around the block a few times. I had taught at a number of universities. So he was a junior, but he came in and stepped up like a senior and has been running well ever since. Dr. Sengupta, thank you for your contribution to this university and the community of mathematical scholars. Now, today, there are a lot of things people talk about in mathematics. Mathematics is such a huge field. And my question was, what can you do successfully in just a few minutes? And so that was a problem. And so what I wanted to do, I want to reflect on a few of the beautiful jewels that I've run into in the mathematical sciences that just really turned me on about mathematics. I became involved with mathematics when I was in college. And what happened when I was in college was I took chemistry. And I was thinking that I probably will be a chemist, a physicist. But my chemistry professor said, to be an excellent chemist, you must be a very good mathematician. So I started studying for mathematics. And when I got to my junior year, I had more toward a major in mathematics than I did in chemistry. So I became a math major. And it went from there. Now, the question to everybody is, what is mathematics? Well, mathematics does not have, there is not a precise definition of what mathematics is. Mathematics, we can give you a nice generic definition. We can tell you that it's an interdisciplinary language and tools where we study abstraction, deductive reasoning, quantitative numbers. We can throw all kinds of things out there. And these will include things that we do in mathematics. And the question is, how does mathematics fit in the body of knowledge that we study all over this, everywhere we go? And one of the fascinating things we can tell you about mathematics is that it is one of the fundamental building blocks of all knowledge. Any educational system has mathematics as its cornerstone. Now, one of the things I thought was very excellent about mathematics, I was a student, but I was a fan of Bertrand Russell for a many times. And he said that in number 4, that mathematics may be defined as the subject in which you never know what we're talking about, nor whether what we're saying is true. Because we don't talk about any particular thing. We are talking about ideas, abstractions, etc. So you might not know this. Now, one of the things I want you to know very quickly is that mathematics not only is it the fundamental building block, but it has been around for a while. Mathematics was only seen, we have evidence that it was only seen 5,000 years ago when the Sumerians were doing mathematics, reading, writing as a discipline. But we even have greater evidence that it was on the scene 20,000 years ago in Africa with the Ashanti bones. They were doing mathematics with these things. So mathematics has been in the process for so long and for doing so many things that we want you to just look at it and enjoy it. Now, people get caught up. What is mathematics? We talk about pure mathematics or applied mathematics or pure and core mathematics and all kinds of things that we'll do. And we have all kinds of disciplines here that we could go through and listen to quickly. But what I'm not going to do is, Miss Henton, is she still around? She's gone. Okay. Now, I would like for only those of you who are going to seriously deal with mathematics to take one of these. Now, those of you who are spectators and not going to seriously deal with mathematics, do not take one. And our feeling will not be hurt if you don't take one. But this is just to break down and give you insight about mathematics here. Because what we want to do is to go to the first jewel in mathematics that we think you need to know about and that you ought to know about, and how things go as we move about things in a certain direction. And so, I should put this thing on here rather than on my draft. So the first thing we want to talk about today is what one of the real jewels that I came into in the mathematical sciences world, we call it the Euler identity or the Euler equation. Now, here's the equation there. E to the I pi plus 1 is equal to 0. Now, some of you might have stumbled over this, and you might not have ever seen it. You might have said, what is this all about? Let's tell you why it is a great jewel. Number one is, E is the what? Euler number is the base for natural logarithms. I is the imaginary unit for what? Complex numbers. Then we have pi in there, which is the what? The ratio of the circumference of a circle with regard to its radius. Now, someone say, of all the equations in mathematics, this one here has some very, very fascinating things in it that you can't find in any other equation at this level. First of all, the number 1 is in there, which is the multiplicative identity. You have pi is in there, which is this ubiquitous number used in Euclidean space and analytical mathematics. You have E in there, the natural logarithm base. And you also have in there what? You have in there the numbers of, you have I, and you have that this is a field here for this. And you have both of these transcendental numbers, E and pi, which play all over the place in mathematics. Now, when I was looking at this, I said, well, this is fascinating to me. Does anybody else think it's very fascinating? Well, there were 3 or 4 people that I was very fascinated to get their comment. There was a fellow at Stanford said that it was like a Shakespearean sonnet that captured all the beauty that one would like to find in mathematics. There was this fellow who had written about Euler's work at the University of New Hampshire. He thought it was an exquisite beauty or one of the greatest things you could read in the mathematical sciences. And then he came up with the fact that there was this Benjamin Pierce who said, it is absolutely paradoxical, we don't understand it, we don't know what it's about, but because it can be proved, we know it's true. So we'll leave it there. And the other two people I want to quote very quickly was that they went beyond just themselves, and mathematical intelligence in 1990 named all identity as the most beautiful theorem in mathematics. And in 2004, you had the physics world saying that it was the greatest equation ever other than Maxwell's equation for electromagnetism. So, now, let's go back up and see what what was the all of identity and what is it all about? We said that's what it is there. What you think about it? Well, first of all, if it's an identity, I can prove it's true in 1 minute. And that's what we will do at this point. We're going to prove that this is true in 1 minute. Now look at that identity very closely, if you will, and look what we're going to ask you to follow us in doing. In looking at that identity, let's tell you that first of all, it started with Euler's formula where he was dealing in from complex analysis. In complex analysis, he told us that e to the ix is equal to cosine of x plus the I sine of y, where we're using these trigonometric identities and we're given the, not in degrees, but in radians. We're doing that. So, once you do that, then what do we notice? That if we look at the radian, if we look at x equal to pi, which is 1/2 180 degrees, then what? E to the I pi is equal to cosine of what? Pi plus I sine of pi. Now since the cosine of pi is equal to -1 and the sine of pi is equal to 0, what does this identity carry us to very quickly? What is the next step that it carries us to? That e to the I pi is equal to -1 times 0 times I. And if we take that and simply what? Put it in the neatest form, what do we have? E to the I pi plus 1 is equal to 0. One of the most beautiful formulas in mathematics, Euler's identity, we proved in 1 minute. Now, we also have here that that's not the only one we want to do. In fact, we had so many that we had to decide which one of these we wanted to do next. Now, I'm going to do this one here next because of time and because of the fascination that I had with this one. And that is Pythagorean theorem. The group of Pythagoras, they did a lot of good basic mathematics, and they sat down and really got involved with that in certain ways. And of course, the triangle and the circle are the most celebrated of all the Euclidean pieces in mathematics, in Euclidean space. Now, Pythagoras' theorem says that a squared plus b squared is equal to c squared, where c is what? The hypotenuse, opposite the right angle. It said that the longest side of a right angle there, we have what? The Pythagoras theorem, and this is square of the hypotenuse is equal to the square of this. When they discovered this, they were shocked. I mean, they kept it hidden for years before they even were able to talk about it, because they didn't want people to think they were stupid or didn't know what they were talking about. But when they got it together, they did. Now, what they are saying here is, if you take that, if you take the hypotenuse there, what do you do with the hypotenuse? If you take that there and you square that right here, the hypotenuse, and you square A and you square B, it is equal to C squared is equal to the combination of both of those squares together. And they didn't understand why such a simple thing they have been looking for years. They didn't know how they came up with this identity. And so, how they came up with this here. And it ended up being very fascinating what they did, because as you know, there is so much there that you look at the algebra of this thing is that if you're given any triangle that's a right triangle, you know any two parts, you can solve for what? The third part. But the reverse also happens. If you know the numbers, the three numbers on a triangle, what you can do is you can actually decide whether or not it is a what? A right triangle. You don't even have to notice a right triangle, but you can prove that is the case again. Now, the question comes is, what do we have here? And one says this: can you prove the Pythagorean theorem? You've used it, you heard about it, you dealt with it. I can prove it in 1 minute. Now, you say, okay, prove that Pythagorean theorem in 1 minute. And all I want to do is basically say, behold. Now, if you look at the blue square, and we need to do something to make that blue square look good. No, we made it look worse. Okay, if you look at the blue square there, it encompasses what? It encompasses a red square and what? 4 right triangles of the same size. That's what it does. Now, what happens there then? If you look at that, if we go back up there and just tell you this thing here, then we're saying to you that the area of the blue square, which is the largest square, is equal to the area of the red square, which is the smaller square inside, plus the what? The sum of the 4 right triangles. That's what we're saying to you. Now, and to show you that, what we did was we took the area of the what? The blue square on the left, and we have what? It's a plus b times what? A plus b squared. Which gives us, when we carry it out, this is what we get here. When we carry it out, you have a plus b squared. Then you write it out this, and you get a squared plus 2ab plus b squared. That is the what? That should be the blue triangle, not that's the blue triangle area. Now, what is the red triangle area? It's simply what? C squared, because it takes C all around, correct? Now, you got now the what? 4 right triangles over there. And the area of a right triangle is simply what? 1/2 the base times the height. And if you got 4 of them and you multiply 4 times what? The right triangles, you end up with what? 2 what? AB. So you got the blue triangle here is equal to C squared plus 2AB. And then you end up with what? Once you take 2AB, you got a squared plus b squared over here on the left side, then c squared plus what? 2ab minus 2ab. And therefore you end up with what? A squared plus b squared is equal to what? C squared. C squared, which is a proof. Pythagorean theorem. Now, and have I used up my 15 minutes yet? I have one more I want to show you, but if I need to cut it, I can cut it. Okay, thank you. All right, now, what we have next is, the question is, what is the difference between, we often talk about, a lot of us, we go around and talk about, how do we know how to distinguish between discrete mathematics and continuous mathematics? Well, there are a lot of things we can do or say about it, but there's just a few fundamental things. Continuous mathematics, roughly speaking, is based on a continuous number line. Almost everything you do in continuous mathematics, you can map it to the real line, or better still, to just a small portion of the number line, from 0 to 1. That's what you can do. But now when you come down to discrete mathematics, you cannot do that. Discrete mathematics does what? It maps to the natural numbers. And they're distinct. Now in discrete mathematics, you go from one to the next, and there's nothing in between. In continuous mathematics, you go from one real number to the next real number, and there's what? Another real number in between. In fact, it's a what? An infinite number of real numbers in between. And that's the thing that really disturbs it to a great degree. Now, and it comes down here, and we get this. Now, if you look at here, this tortoise here that we have here, it's a topological space that we can deal with through continuous mathematics. The graph at the bottom is the typical way we deal with what? Discrete mathematics. We relate one by distinct objects and the other one by continuous objects. And this is the thing that happens, and then when you go ahead and look at this, in general, continuous mathematics uses the tools of the calculus, which involves the concept of the limit, the concept of continuity. It deals with differentiation, integration, the rates of change, and discrete mathematics does not. It deals with discrete objects. And in discrete mathematics, we do things in what we call using what I like to call recurrence equations. We define one term by what? Previous term. But in continuous mathematics, we use the tools of the calculus to do what we need to do and what happened there. Now, and I'm going to end here, and I'm going to try to make this thing, what happened to it? There it is. The thing that's fascinating to me how this happened, or how it looks so great to me, is that as you look at this, and you talk about what you call the area under the curve, how we can measure the exact area under the curve using continuous mathematics, using the calculus, the definite integral. Now, but there is a thing is, we can take the recurrence equations of mathematics, of not mathematics, of discrete mathematics, to do what? We can approximate that curve, the area under the curve, by using triangles, trapezoids, or rectangles, or what have you. But we can never get the exact amount with discrete mathematics. But we can get the exact amount with what? Continuous mathematics. Now, question is, there is one curve by which we can get the exact area under the curve using discrete mathematics and using continuous mathematics. Who knows what that curve is? Where you can get the exact area under the curve using both continuous mathematics and discrete mathematics. Well, we ended by telling you this. It is when the curve is a straight line. You can get the exact amount. Now, I'm going to end here, but I got two things I must say as we end. There are 2 or 3 groups now that are getting $1 million prizes for people who solve certain mathematical problems. And they gave me the authority to give out $1 million prize here for anyone who solves this problem. Do we have a yardstick here anywhere?
You need a point.
Yeah. No, this is,
Yeah.
no, I need an actual yardstick. Well, it doesn't necessarily have to be a yardstick, but take it here. And this is the problem. It's called the Zeno paradox. And what you do is, Zeno says that he wants you to take something here, and he wants you to have it on here, and you have one of it at the edge of the table. He said he wants you now to take it and take 1/2 of it. Each time he wants you to take 1/2 off the table. And then you come to here. So you have what? 1/2 on and what? 1/2 off. Then he wants that which is left to take what? 1/2 of that off. Good. And he says that anybody who can get it done before they're 75 years old, they get a leave. So anybody would like to try for the $1 million while you're young? Thank you for the opportunity to present.
Thank you, Dr. Houston. That was really pleasant. Our next speaker is our very own Dr. Vinod P. Manglik, Professor of Mathematics and Statistics here at Elizabeth City State University. He got his BS and MS from Lucknow University in India. He also holds a professional statistician certificate and a diploma from the Agricultural Institute of, an agricultural statistics diploma from the Indian Agricultural Research Institute. He got his PhD in statistics at UNC. He has taught at universities in India for over 20 years, and we are fortunate that he has been at Elizabeth State for over 20 years. He is the principal author of 2 undergraduate statistics texts in Hindi, and he will be bringing us the enticing title of Some Tidbits in Mathematics.
Four slots, one not occupied.
Oh, yeah.
Okay, so first of all, I must thank the organizers for giving the opportunity to see all these people and sort of celebration situated by Dipendra Sengupta, one of the oldest colleagues in the department. And he is just my younger brother. And I think he also thinks the same way. Okay, so then I was approached by organizers to do some talk. I said that if somebody else is there, give them a chance. I want to skip that because I'm not a very good speaker. But they said, okay, it will be good if you speak. I said, all right. Then everybody started, what did I say? What's the topic of my presentation or the talk? I thought about it, I said, because long back in 1964, one of my colleagues said that to prove the existence of God using the spirit of reductio absurdum, contradiction. God doesn't exist, to suppose that, then who created that, who created that, who created that, it is the end. You show that the law of God exists. Then the second thought I got, I think the number 0 or the empty set is like the God of mathematics. It exists everywhere. Satisfy the property of the number 0. Then I thought they are very small things. Let me talk something else. So I thought of some tidbits in mathematics. Sometimes think that should it be tidbits of mathematics or in mathematics? So anyway, I thought let me keep it in mathematics. So first, I'll talk about some interesting problems. I have about 20 minutes, so maybe some time I will spend. First problem is this. Scientists are playing the game of hide and seek. Einstein was the seeker. Newton did not hide. And he stood in a square of 1 meter. So literally Einstein found him and said, Einstein said that, Einstein, I found you, Newton. I won, you lost. What did Newton say? Newton said that you are wrong, Einstein. I am not Newton. I am standing in a 1 meter square. And in Newton, 1 Newton per square. Is it fast? Am I there? I'm not Newton, I'm Pascal. So here, all of you can try this. You need a calculator. Multiply your age by 39. Don't delete it, keep it there. Then multiply the product 259. What do you get? Your age, different places. Am I right?
Oh, yeah. Yeah.
So this will work for all the cases where your age is 2-digit number. The idea is this: if you multiply these two numbers 39 and 259, what do you get? Multiply numbers 39 and 259. 10101. Multiplied by x will be x will be repeated. So now try these numbers. Multiply these numbers. They are prime numbers. Bigger strict 101010. You can make the column more difficult to utilize. So this is that 10101. If you want 3-digit number to calculate 1001001, find the factors of those. Here another interesting problem, because my talk is required in mathematics. No prerequisite. A farmer had 17 cows and 3 sons. When he died, his will was that he gave one of the cows to the eldest son, 1/3 to the middle son, and 1/9 to the youngest son. 17 cows. After the will was read, there was big confusion, there was big silence. How to make the assignment as R. And then elderly man distributed those cows. How did that? One we thought. The clue is that 1/2 plus 1/3 plus 1/9 is not 1. This common denominator is 18. 2, 3, 9, 1 half, 1/3, 1 9, did not 17. So what he did, he looked at those numbers, 1 half, 1/3, 1 9. So he looked at those numbers, did that calculation in his mind, what of the two, went to his board, got 1 cow. So now 18. Half of that, 9 to 1, 1/3 to that. They add up to 17. It is now back. So same thing, you can extend over 23, you can find, you can divide that so much, but the common denominator is not 23. You can extend to more different cases. Simple or better. This common denominator. Another one. I discussed most of the problem with Dr. D. Except the one, first one, the age one. It is not that easy to say. First of all, write the number TSTWO. You can go on the paper. Right? Spell out TSTWO. Divided by 10 TEN. Right? Cancel out T. So WO over EN. Now alphabetical coding. W is 23rd letter. /23 plus 15. W plus O, 23 plus 15. So when this problem was put at some gathering, everyone said, it's crazy. How will prove that? The Parliament of India shows and prove that. So that's the first part. Some interesting problems. There are many. So I have been discussing time to time, as a D, we talk about Paul Adams. Whenever I see his photo, I think I have seen Paul Adams. Then I record in Chapel Hill towards end of 60s, we had the conference of commutants, organized by Professor R. Bose. And at that time, I saw him. And my task was to take their notes and prepare health and proceedings of that conference. You know, those days, nothing but everywhere. I used to hear his tapes and tape them onto the spool type of small tape recorder. From there, transfer it to big spool thing, and then listen to it, and then try to write something. Some of them we are, so that's where I remember that I saw Paul Erdogan because later on I saw that he worked on a result by Bose Canadian partner on CCT of Poynter's conjecture. I'll come to that. So that's the way I got, so that it, then I thought, okay, I have seen Paul Erdogan. Then I got interested in this genealogy project of mathematics. Then when did he die? Then it occurred to me that I have seen Jerzy Neyman also. We have heard the name of Neyman-Peterson theory testing hypothesis. So then, because we're very tall, we had probably in 1967 or 68, we had a conference in sampling in Chapel Hill again. So that time it was held in the Graham Hall, the old student union. These three were walking, Neyman, Frank Yates, and one of his students, Dr. Sohini. So then I thought, okay, let me go and do some search in that, what we call database. First I began with this. Jerzy Neyman. Date of birth. He joined Berkeley in 1945. Worked till 79, 81 he died. So, his PhD in 1924, University of Warsaw. I could not get translation of this in English. I tried German, Polish, and could not. But looked like a Polish university, scholar, advisor. And then his descendants. So you see, this P.V. Sukhatme, Indian first student of Dr. Neyman. He did, when he was at Cambridge, University of London, then he did his PhD in 1936. He has no, go to thesis, PhD thesis of Neyman, deals with agricultural experimentation. He is the founder of sampling theory in statistics. He applied to this agricultural experimentation, agricultural experiments. So that's why, so P.V. Sukhatme did in 1936, then he came to India and he was assigned the director of the Statistical Institute in Delhi, in the British time. The institute was formed, he worked there, and then he spent most of his time in FAO, in the type of FAO. That's why he doesn't have any experience. And then you see Lemon, another guy at Berkeley. He has 925 descendants. Then I thought, okay, we have 43 students. What about others?
George Dantig was the
Say it again?
George Dantig was the father of linear programming.
Yeah, Dantig, he came to this.
Yeah.
Okay, so that's about, I thought it was a very large number. So let us not forget errors. Let us see what happens to them. Is statistic, PhD 1934. I think I got this translation. Only 144 descendants. Then I thought, all right, let's proceed further. I'm really time. So I got sort of addicted to that project. This is Sir R.A. Fisher. I treat him as father of statistics. Which is done. He has beard like Richard. See this, always you see his photo with his beard. I'm seeing that Cambridge, 1926. Gene is the two advisors. Stratton be here in mathematics also. Descendants. Dominance first was D.J. Finney. He worked in biological statistics. His book, Statistics of Bioassays, is a classical, that was to be classical at that time. Then CIP, etc. started. First PhD, then our own CRR. Did PhD, did is Fisher in 1948. And Owen is another good statistician. No, much more. I missed something. Not more. It was a few hundreds. Okay, I thought that we go to CRO. He is, I would say, the topmost statistician from India. First student, Deva Basu. He worked with ISI most of the time. The second is my advisor. They did 53 first student, 58 second. Then I have this name Pramod Pathak. He was 2 years senior to me at Lucknow University. He did masters in 1959. Then he joined ISI, where CRO was there to do PhD. Within 1 year, he published one paper in the top reputed journal of statistics, Sankhya. And for in PhD, in 4 years, he had 6 papers. And then he moved to University of New Mexico, and now he's attorney in Princeton.